Yeah, good evening everyone. So this is Samrat Das, PhD student in the Department of Electrical Engineering, IIC Bangalore. So we'll start afresh today our course. So the course title goes by DC machines, magnetic field distribution, dynamic modeling, power electronic control, and simulation using MATLAB Simulink. So that is the course title. So we'll so our focus is on DC machines, and the various topics that we are going to discuss are basically magnetic field distribution, dynamic modeling, power electronic control, and simulation of the entire system. So in this lecture we'll go through all the topics and have an overview of all the things that we are going to discuss and a brief basic understanding of all the topics. So we'll start with the first one, that is magnetic field distribution. And magnetic is specific to one kind of field. So field is the most basic word. So we'll start with understanding field. So when as soon as a layman, when we hear the term field, what comes to our mind? So it's some kind of space where something is distributed. So field refers to basically a space and some kind of distribution of some quantity. So the most basic example or most well-known example or well-known example of a field is basically a paddy field. So what we mean by that? There is a space, there is some land where there are many paddy uh, grasses there. So that is distributed. So that is the distribution of paddy grasses in a land mass of area. So that is what we mean by paddy field. Now when we come to science and engineering, field can be distribution of certain quantity, and that quantity, so field is basically distribution of certain quantity, and that quantity may be scalar or it can be vector. What do we mean by scalar? That it only has magnitude, it does not have any direction. But vector, it has magnitude as well as direction. So when we talk about distribution of certain scalar quantities, then we will understand, so we understand by that that there is a space, and at each coordinate the magnitude is different, or magnitude is basically distributed, and that is what we mean when we tell scalar field. So an example is the temperature field. Temperature field is an example of scalar field. So there is a space, so suppose there is some hot body. So this is hot. So all around the space, this is a 2D space that I am talking about. So all about, in the x and y direction, the temperature the temperature will be different. So there will be layers of constant temperature regions. So the distribution of temperature, if we can represent it by, if temperature is the quantity, that is a function of both x and y, which are basically the spatial coordinate system. So here on every point the temperature, there is certain value assigned to it. Now when we go to vector field, vector means it does not only have a magnitude, but it also has certain direction. Say the first vector field that we have come across is, say, gravitational force, the field of gravitational force. So if there is some mass, say m, in a field, for simplicity I will deal with 2D coordinate system itself only. So it can be 3D as well. So if there is some mass, that mass will attract the other masses by certain force, and that force will be quite strong nearby the object, and it will basically decrease as you go away from the object. And also at any point, suppose I am at this point there is some force, gravitational force, that any unit mass will experience. and there is a direction to the force also, so it will be towards the body. So a vector field, basically in this case is a gravitational field, gravitational force, so say F gravitational force. So that is again, that is not a scalar field, that is a vector field, and that is some function of
Sir,
x
sorry
and
to
y.
interrupt you. Sir,
Yes.
the screen showed that the screen recording has been ended. Could you check that once?
We can see the screen, sir, you are sharing.
No, no, it's being recorded. So I have turned up the this transcription, not the recording. So recording is still going on. Yeah,
Okay, sir. Okay, thank you.
Thank you.
yeah. So I was talking about gravitational force and its field. So first example is a gravitational force, the field of that, the distribution of gravitational force at different points. So here you understand, at every point there will be certain magnitude to it and there will be certain direction to it. Another example can be electric field. So the mass will be just replaced by some charge of q, coulomb. Then if there is certain other charge, other say unit charge, that will also have some so this is the same space, only the point mass or the mass I am replacing by certain charge, right? So if there is certain unit charge, it will experience certain force, and the only change from gravitational field is it can be attraction as well as repulsion based on the sign of the charge, right? So electric field, the force due to electric field is another example of a vector field. So again, at any point the electric field can be represented by a vector that has certain magnitude and certain direction assigned to it. Now we will go to the example of a magnetic field. Magnetic field, what is it due to? It is due to certain magnet, presence of certain magnet, and it will also have its field of attraction or repulsion force to any other magnet. So magnet can be electromagnet. So any magnetic field, the production of magnetic field can be due to certain permanent magnets. So what do you mean by permanent magnet? They have some the object, the property of the material itself. It is basically polarized and it has some north pole and south pole. It is a magnetic material that will attract any ferromagnetic material, and yeah, that is what we mean by permanent magnet. And it can be due to electromagnet also. So electromagnet, what is that? If we have some current flowing through any conductor, or if we have some current, there will be certain electric or certain
Your voice is not able to audible. Hello.
Samrat, you are muted.
Yes. No, again, it's going to mute.
Am I unmuted now?
Yes.
Okay. So if there is certain current, there is certain current, constant current flowing through some conductor, then there will be some magnetic field around. So that is, it's a magnetic field distribution. So we are going to start with, so we understand what we mean by field, And what are the different types of fields, a scalar field or vector field. We have seen some example of a scalar field, that is a temperature field. Vector field, we have seen three examples: gravitational field, electric field, and magnetic field. Only three examples as of now are enough. So we understand what we mean by magnetic field. If there is some current carrying conductor, some current, steady current through any conductor, then there will be some magnetic field around. And how to know about the direction of the magnetic field? If we know that right hand rule. If we basically have this, if we have our right fist of the right hand, then if the thumb points towards the direction of the current, then the other fingers will be pointing towards the direction of the magnetic field. So if we have thumb like this, then other fingers are like this. So if this is our current, so in this case this is the dot current, so there will be magnetic field around this in the anti-clockwise direction. So that is what we mean by that rule simply tells us about the direction of magnetic field. And you know that it will be stronger nearer to the conductor, and it will be weaker away from the conductor. So that is what is shown here: magnetic field due to a current carrying conductor. So at the center of the screen you have a conductor that has some current flowing through it, and the field lines, the flux lines, are basically shown. So this is a representation. So if we have to represent magnetic field, what are the ways to do that? So any field can be represented in a vectorial way, vectorial form. So at each coordinate system you indicate the direction with an arrow, and say so inner side you draw bigger arrows, and as you go away you keep on reducing the size of the arrow. So the magnitude of the vector is represented by the length of the arrow, and the arrow head that indicates the direction of the vector field. So similar to that, magnetic field can be represented like this. So there is a this is the vectorial representation. And we see there is another way of representing magnetic field that we see here with lines. So these are basically the magnetic field lines. And how do they tell us about the direction and magnitude of the magnetic field? So if in a certain region the density of the flux lines are high, then that indicates that it has high flux density region, that is high flux density region. And at any point on the flux line, if we draw a tangent, then that tangent will tell us about the direction of the magnetic field. So this is the simple way of representing a magnetic field through flux lines. So because vectorial way of representing may become little clumsy, because we have to draw so many arrows and then vary their lengths as well, which can become little clumsy to represent. So we find that flux line distribution is quite handy to represent such magnetic fields. So here you can also look at certain properties of the field lines, like all the flux lines or field lines. So I'll use field line or flux line interchangeably. So all the lines are basically enclosing the source, that is the current carrying conductor. That is one of the properties of the flux lines. Then next property, you can see that all the lines are basically smooth. They do not have any discontinuity at any point in the space. Then another thing that you can see is yeah, these are the basic properties that we want to focus as of now. We will see what happens if some other ferromagnetic material medium basically comes into the picture. So another thing is quite visible from the color plot as well as the flux line distribution also, that nearer to the conductor it's deep color. That means it is high flux density region. As we go outward, in the outward direction, the intensity or the flux density basically comes down. Now this is about the single current carrying conductor only. This is like a long line. So if we have a long line and some current flowing through it, then there will be some distribution of flux line around that. This case is representative of that. Now what happens if we have two long lines side by side going, and having current in the same direction. That then this is one conductor, and left hand side this is another conductor, and you can see that even in this case all the lines are enclosing at least one of the conductors, and most of the lines are enclosing both the conductors, because their fields are basically aiding when you are going out. When as you are going outward, the the two conductors are the they aid the field at that point. But if you look at the field at the middle, that is in between the two conductors, you can understand that if one is dot and another is also dot, then both will have counterclockwise direction. So if you are at the middle, one conductor, the left conductor causes it to be upward, but the right hand side conductor causes it to be downward. So if both currents are exactly same, then at the exact midpoint you will have a zero flux density region. That is where the point where the flux or the field due to one will exactly cancel the other. So you have zero flux density region. But as you go out, you will see that flux lines tend to become concentric circles, which is similar to when you have only one single current carrying conductor. And that means when you are at certain distance, say r, which is very high compared to the distance between the two conductors, say d, then effectively your system looks at the total enclosed current. So here it is I plus I, that is 2I, and your field will be similar to a case when there is 2I current flowing through a conductor. So that is the thing. Next we'll go to a case of a turn. So if we have, say, certain, if we have some bobbin kind of a thing, and say so this is a cylindrical thing, and we are having some current, some conductor going like this, and it is going all around the other side, and it's coming back like this. I think you are able to visualize the what do I mean by this. So if we look at it from this side, then on this side there is some conductor has some cross sectional area, and this is having current that is if we look at it from that side, then it is going actually right hand side, or into that surface, and on this side it is actually coming out of this surface. So this case can be represented by this this figure. So one side it is going into the board, that is, or into the screen, that is basically your cross conductor, and the other side is coming out from the screen, so it is dot conductor. So this is the case that we are having here, and because in this case cross conductor will have clockwise direction flux lines, and anti-clockwise and dot conductor will have anti-clockwise. So you can see that at the middle, in between the two conductors, the field due to both conductors basically aid each other, so they become strong, it becomes stronger. So that is what you can see here, flux line density is quite strong as you are in the middle. So one thing you can understand, that why do we make turns in when we want to have some magnetic field. Well, we generally have some coil, because if we have a coil, then in the at the middle of the coil you have quite strong magnetic field. Now I'll remove this part and go to the next case. Okay. Yeah. So here I have three conductors, or basically three conductors on both sides carrying current in the opposite direction. So here you have current, say in the dot or cross, whatever direction you want to consider. Say all the left hand sides are having dot current, and all the right hand sides are having cross current, right? So because of that it will be, so all the dot conductors will be aiding the flux, and so there are basically multiple turns. So basically at the middle here you had only this much area where you have some kind of constant flux density region, but as you go on adding number of turns, then you can visually see that at the middle of the coil, basically at the in between in the coil, basically if it is circular like this, you have turns, 3 turns like that. So in between you have high flux density region. So this is what is called a solenoid or a coil, and it is only a non-magnetic former around which we are wounding the coil. So it is a air core coil basically. Now let us try to understand what we mean by magnet, basically the axis of a magnetic field. So, or axis of a magnetic field due to a coil. So if we have a coil, then we can, if we have the flux line distribution also as we have in this case, it is possible to draw an imaginary line at the middle which is not crossed by any flux line. None of the flux lines intersect with this line, or they cross this line. That is what is defined as the axis of the magnetic field. So for this case also you can see at the middle of the coil, there is we can define, we can draw an imaginary line which is not crossed by any of the flux lines. So uh, that is the axis. So you understand the axis of the magnetic field, and based on the basically the polarities of the currents, it will be upward or downward. If it is say dot conductors on the left side and cross conductors in the right side, then with right hand side rule you can see that your thumb points upward, so the magnetic field axis is actually upward. I think this is understood. Now we'll go to the case of magnetic field due to iron core coil. So what do we mean by that? So we were winding some coil around some bobbin. So it was like this. It is a coil like this. So earlier it was some non-magnetic material, say plastic or rubber. It can be anything, any non-magnetic material. But what happens if we wind some conductors or some coil around magnetic material? So that is the case which is shown here. You have a bar ferromagnetic material. So this can be iron, cobalt, all ferromagnetic materials that you have, any ferromagnetic material or steel, any kind of ferromagnetic material it can be. And if we actually wind some current, wind some coil around it, then you can see that at the middle of the conductors you have quite high flux density. And if I just quickly go back to the earlier case, you can see electrically speaking it is the same thing, but with putting the bar ferromagnetic material, what we are doing, we are trying to align the flux lines along the ferromagnetic material, because ferromagnetic material provides highly permeable path. That is, it is having newer value in few thousands, so 10k or even higher. So that is why most of the flux lines they are aligned to flow along that, because that is more or less resistive from electrical circuit point of view, that is less resistive compared to flowing through air. That is why by putting any iron bar, you can basically align more and more flux lines along the direction, along the geometry of the iron bar. So next, if we go to the next case, if I extend, I just want to show what is the effect of extending the iron bars on one side. In till this point you can see that on both sides, on the left hand side as well as right hand side, the distribution is uniform. But as soon as the iron geometry, basically the iron bar that we are inserting, that is like a C shape. So that is basically having some extensions on the right hand side. So you can see that most of the flux lines, or more than half of the flux lines, are basically having a bend in the right hand side direction. And then after when the iron path is done, then they are completing their path to the the air regions. So that is that is basically telling us that if we want to make flux lines flow through certain region, then we can basically plan the flux lines by putting iron around that. So suppose if we want to have closed flux lines like this, then what is needed for us to do? If we extend it in the bottom side and if we extend it in the top side, then more flux lines will tend to flow in this direction and it will complete its path like this. Let us see that. So this is the case. If we extend the C core to become almost a closed C core with a small air gap, then you can see that most of the flux lines are basically following the geometry of the iron shell that we have added, and because they are forced to flow through the highly permeable iron material, they are so most of the flux lines are are basically guided up to this point. Then once they reach this point, they are forced to come into air, and then as soon as they traverse a little path, then they see some another iron body there, then they are free to enter that, and like this they are enclosing their path. So they are basically closing their path. So one of the most important properties of the flux lines that I missed saying earlier, that all the flux lines, unlike electric field lines, it has to be a closed line. So it has to be a closed curve, and they have to enclose the current carrying conductor that is the source of it. So we can see that, and this is actually a very important geometry in sense, or basically important structure, magnetic structure, when we talk about electrical engineering, magnetics, etc. Because here what we can do is we can predict the flux lines quite easily, and we can produce some high flux density in air gap. If you see in the earlier case, high flux density was mostly appearing within iron, because iron is more permeable, and in the air, in most of the regions, flux density was quite low. In this case also, that is the same case. In air gap, in air regions, flux density is quite low. But if we have our iron geometry so that there is only a small air gap, and the flux lines are guided by the iron geometry to flow through it, then we can have a quite high flux density in the air also. Why is it important? Because now I will introduce another. Till now I have been talking about the magnetic flux density vector only. So you know that from basic electrical engineering, or before that also, you have another magnetic. This is the magnetic flux density vector, and this is the magnetic field intensity vector. And how are they related? Basically, B is nothing but mu into H, and here mu is basically the permeability of the free space and the relative permeability of the material. So for iron, this value is quite high, but for air this value is 1. So what happens? So if we have but high permeability, that will attract more and more flux lines towards it. But air, if it is because it is low permeability, it will not flux lines would not like to flow through it quite with a very good density, right? But if we have a geometry like this, where all the flux lines are forced to flow through the iron geometry, and they are forced to cross a small air gap, then what we are ensuring that there is a very high B in the air gap. And along with that, if we have a very high B in the air gap, because we have H is nothing but B by mu naught into mu r, and mu r is equal to 1. So we have a very high H also. That was not like the earlier cases. So in this case, if you see, H in air was quite low. uh, H in iron is naturally low because H is basically B by mu naught into mu r, and because iron has high mu r, so even if it has high flux density, because of very high mu r, H value will be quite low. But in this case, because we are aligning all the flux lines to flow through the small air gap, we have very high B in the air gap, and naturally we have very high H in the air gap also, and the energy stored in any magnetic field, that is measured by half BH. So you can see that we have high B value as well as high H value also, so we can store some good amount of energy in this small air gap. So that is useful when we are making some inductor, or that is the main reason why we keep a small air gap for energy transfer between the stator and the rotor in an electrical machine. So now, as we understand how to produce a very high, very strong magnetic field in a small air gap, and what is the utility of it. So basically we are producing a very high magnetic field in a small air gap, and next I will try to show you that this case is similar. Basically, what is the purpose of that? What is it is producing some magnetic field. And if you know from basic electrical engineering, in DC machine you have two parts, one stationary body, another rotating body. So you have stator, that is the stationary body, and there is field winding in the stator. So the name itself suggests to you that field winding, what is the purpose of it? Purpose is to produce a magnetic field there. Where to produce the magnetic field? It is supposed to produce the magnetic field in a small air gap. Now, because the stator has, basically it has stator, it has rotor, so there are two bodies. Let us try to redraw this structure in a sense, so that we can basically realize the stator of a DC machine from this simple structure. So say the same thing basically I am drawing as of now. This is the core, right? This is the core, and say we have 4 turns, say dot cross, sorry, dot cross, dot cross, dot cross. So we have a high flux density, and say we need two bodies, right? One is stationary and the other will be rotating. So we just, as of now, will put some body, and there will be some air gap in between. So if we have this structure, so this is separate from the stator that I am trying to draw. So this is the body, and we have very high flux density in these regions, right? That is well understood from this picture that I have on this side. Now I can simply modify this geometry, say to make it more symmetric. Let us extend it on this side, on both sides basically, right? So this is what I am doing. So I'll erase a little portion of it to avoid any confusion. So this is the geometry that we are having. I'll try to make everything in red. Right? So this is the geometry that we are having. But here what is happening? This is the source of the magnetic field. Some part is basically flowing through it, and some other part is basically flowing through it. But our purpose is to produce high magnetic field in this region. For that, what is required? For that we need the source to be in the middle limb. So what we will do, we will try to have inward flux flow. So in order to have it, we will simply put the conductors and basically distribute the conductors here, rather than limiting the conductors within one limb. So I will erase those portions. Yes. So if we have cross here, then it is downward. So we have cross conductors, dot conductor, cross dot, cross dot. So you can verify that for this type of distribution also, we are having all the flux line distribution in the downward direction, and after that half the flux is going and completing its path in the left hand side limb, and another half is basically flowing and completing its path in the right hand side direction. So this is the geometry that we have as of now, and if we want to have almost uniform flux density in all the portions of the iron, then what do we need to do? If we just see this portion, if it is carrying some flux say phi, then this portion, this one limb is flowing phi by 2 and this is flowing phi by 2, and we know that P equal to, what is that, flux by cross sectional area. So if we want to have the same B, so wherever we need to have half the flux, there we can reduce the cross sectional area to half. So simply we can do that. I will just erase the outer one, right? So if it is like this, I can simply reduce it to half to have almost uniform flux density throughout the regions, right? Here, yeah, it's almost half, little lower than half, but yeah, you understand what I mean to tell. Now, is it actually having uniform flux density in all regions? You can just look at the right hand side, left hand side picture. You can see that in this region, if I try to draw a line here, in this region, that is in an iron limb, if we are at the middle, then you can see that flux density is almost uniform as we go. But if we actually go to any of the edges, then you can see that flux lines are quite dense in the inner side, but they are not that dense. Actually, they are quite they are having very low density in the other edge. So why is that so? I have during the telling the properties of the flux lines, I have already told you that flux lines within one medium, they do not like to change its direction abruptly, but this geometry is having some sharp edges. So they are forced to flow, forced to change the direction abruptly. That they will not do. Instead, what they will do, they will redistribute so that they have high flux density in some regions and they will have very low flux density in some other regions. So if we actually want to have almost uniform flux density in a region, what is the best way to do it? If we have certain geometry that is having the least uh, sharp edges or does not have any sharp edges, then our job is done. What is the geometry that does not have any sharp edges? It's the circle. It's the circle that actually does not have any sharp edges. So we can basically change the outer shell that we are having for flux path completion in a circular manner, so that the flux lines are almost uniform in that region, and I'll simply draw it. Yes. Right. With this we have, if we look at any of these cross sectional areas, because everywhere it's very smooth, so flux lines will tend to distribute themselves almost uniformly, and the flux density distribution will be almost uniform, and you will have almost equal flux density in the inner edge and outer edge, approximately. So here is the here we have something that looks similar to a stator of a DC machine. So because we know that we are dealing with rotary system, so we have something rotor that is cylindrical in shape. So I'll replace this inner square kind of a thing, whatever I have drawn, I'll replace it by a cylindrical kind of a thing. Mind you, I am just drawing a cross sectional view. That means it has, whatever I am drawing, that is having some depth in the axial direction. So here we have the pole, and then if we have a circular body, then in order to have almost uniform air gap, then what we can do is we can taper this portion also and make it circular, right? We can make it circular, and if we make it circular, then if I try to draw the flux density, or basically the flux lines in the air gap, it will be something like that, right? So you have high flux density regions only from this portion, in the on the left to this portion on the right. But if we want to have almost or more regions with non-zero flux density, so here what we have, here we'll have some flux density of certain sign, here we'll have certain flux density of the opposite sign, and here in between, in between the two poles, what is called as interpolar region, because interpolar means in between the two poles, that is having almost zero flux density. But if we want to reduce the zero flux density region, then we can also extend the pole on both sides, right? We can extend the poles on both sides, then we can have almost uniform flux density over a long over greater theta, or the for a higher theta value. So if we were having for only, say, this was the angle earlier, say some 100 degree, now we can have it for almost 140 degree, right? So if we have 100 out of 180 degree, if we have high flux density for almost 140 degree, then interpolar region for one side, it's only, say, 40 degree, so 20 degree here and 20 degree here. So we are reducing the interpolar region where we have almost zero flux density. So this is the structure of the field of a DC machine. So we can basically look at a stator of a DC machine. So this is the outer stator. Here I am just putting a cylindrical rotor. I have left some space at the middle because that is basically the shaft, and the rotor, magnetic rotor is basically mounted on the shaft is non-magnetic, so this is as good as air. So that is why I have kept this vacant, magnetic for magnetic representation. And here we are having certain number of turns, say dot conductors we are having, and everything I am clubbing and representing with some box of dot. And similarly this side we are we are representing with some box of cross. Similarly at the bottom we have box of dot and box of cross. So this is a stator, or a representative structure of a stator of a DC machine. And you can see that if that is excited, then there are flux lines. You can see that flux lines are distributed in the air gap. Had we if our pole was limited up to this, then we would have flux density only in this region, and probably because of fringing little bit here, but not as much as up to this portion. So here, because you can see, because of the extension of the poles, that is adding the, this is actually called the pole shoe. Because of adding pole shoe, we are having higher flux density, or basically not, very low zero flux density region. And considering it as dot and cross, it is basically the flux line direction is upward. So if we consider this surface of the stator, you can see that flux lines are entering this surface, and as per the convention, if there is a surface and if flux lines are entering that surface, that is magnetic south pole, and if flux lines are coming out of that surface, then that is north pole, and in between they complete their path like that. So half the flux line is again flowing in the left hand side portion, that is called as yoke, for that is for completing the flux line, and another half is flowing through the other side yoke, and this is how it is completing its path. So we have created a quite reasonably high flux density in the air gap region. But so if our rotor, or in between whatever we have kept, that is also a magnetic ferromagnetic material, then for this rotor surface, you can see rotor surface, this surface, from this surface flux lines are coming out. So here we have north pole on this upper surface, and here in this surface we have south pole. So if we have some north pole and south pole facing together, what is expected to happen? They will attract each other. So in this condition, the rotor will be attracted by the stator, but will it rotate? No, it won't, because the force is in the radial direction. There is no force that is causing a torque. What do we mean by torque? If we have a cylindrical body, if some force is acting like this as a couple, so it is tangential, it is in the tangential direction, right? If it is the surface of the body, the force direction is tangential to it. But so this type of couple, what is known as couple in physics class 11 12, so if we have some couple, then that will lead to torque production. So torque is basically, if this is the force, if radius is r, then torque is basically F into 2r. So that is the torque, and it has certain direction. But in this case, what we are having some force in the radial direction. Similarly here in the radial direction. So this does not lead to any couple production or any torque production. So if we, that is why if we only excite the stator or the field winding of a DC machine, it will not rotate. But at least we have created one field, or we have created some high flux density in the air gap. Now let us see what is actually needed for torque production in a magnetic in an electrical motor. So basically, as the title tells you, we need two magnetic fields. So we already have created one magnetic field. If we have so let us try to see that through examples. Say I have one electromagnet or normal magnet, that does not matter. As of now, I'll just represent it like this. Say this is a magnet. Say this is a north pole, so this has to be the south pole, and say this is stationary. So this part of the this end is basically held stationary, and we have another magnet which has some roller on its back, and this is the surface on which it is stationed, and say it is south pole and north pole here. Now what will happen because of this? There will be some force in the upward direction, in the y direction only, but there will not be any motion in the horizontal direction. So that means if we have two magnetic fields, but if they are aligned, if they are basically aligned to each other, then there is no net force in the horizontal direction. For this case, there is some force in the radial direction or the vertical direction, but there is certainly no force in the horizontal direction, which is needed for it to for this structure to move. Now we create the same thing. Here we have south, here we have north, and we displace this one by some displacement, and this is the south, this is the north. Now what do you think will happen? Basically it will have some force like this. So the force will have certainly very strong very strong vertical component. Along with it will also have some horizontal component. anyway this is assuming that the weight is quite high, and this vertical force cannot pull it up, assuming that this horizontal force, because we have rollers put here, so this horizontal force will try to move this body in the right hand side direction, and it will come in this location as it was in the earlier case, and after that it will become stationary. So, we are able to produce some horizontal force by this type of uh, uh, arrangement. Now, just to complete the thing, if we want to produce some force in the other direction, we have to have the magnet or the moving magnet displaced in the other way, that is we have some north and south, and in this case the force is like this. So again it has some vertical component, it has some horizontal component, and the horizontal component will make the rotor or the whatever the moving object to move in the left hand side direction, and that is how it will come here. So what do we understand from that? If we want to, so this same thing, if it is just drawn in a circular fashion, like if say this is the stationary part, somehow this is stationary, and this is the rotating part, somehow basically we are having something like this, where we have some pin and that is holding it on the ground, so that it cannot move radially but it can rotate. It is free to rotate, but its other degrees of freedom are basically blocked. If we have a case like this, so downward I am not drawing as of now. Only two things, say here we are having a north pole, here we are having a south pole. Now it will rotate. So we need two magnetic fields, basically two magnetic fields we require, but for torque production they cannot be aligned to each other. There has to be some displacement between the two magnetic fields. So the principle for the principle of torque production goes like this: for torque production we need two magnetic fields, and they have to be displaced. They have to be, if the magnetic field in between angle is theta, then theta has to be not equal to 0 for some torque production. If we have that situation, yes, we will have some torque, but after some time, when the theta becomes 0, because naturally because it is trying to be aligned along that direction, naturally it will be aligned, theta uh, will be 0 sometime. If we allow this to rotate, then theta will become 0 and there will be no torque production. So next slide we will discuss what is required for continuous torque production. So we will end by discussing that. So for continuous torque production, as we understand, for anyway torque production we need two magnetic fields. Two magnetic fields are necessary for torque production, but for continuous torque production we need to have the two magnetic fields always displaced with respect to each other. That is, if one magnetic field is say F1 and another magnetic field, the axis is basically F2 and the angle between them is theta, then we need to have F1 and F2. That is mandatory. We need to have two magnetic fields, but along with that we need to have theta is equal to constant throughout the time. So with time we need to maintain the theta to be constant. These are the two necessary things: theta equal to constant and not equal to 0. Right, it can be constant and always 0. That is not enough for torque production. We need to have two magnetic fields, and we need to have some non-zero theta, which is basically constant with time. So that is necessary for continuous torque production, and uh, so we'll just see a few cases how are they basically ensured. So here we have many options. So we can produce two fields, absolutely sure. If we, similar to stator, if we put some conductors in the rotor, we can produce two magnetic fields. But there are three cases, or basically some possibilities or some combinations we can have, with which we can produce we can reproduce this case of having two magnetic fields and having theta equal to constant at non-zero value. So suppose we have two magnetic fields, one is F1, another is F2. Say this is omega 1, this is omega 2, with respect to a stationary object, stationary body, or stationary reference frame. With respect to some stationary reference frame, this is omega 1, the angular velocity, and this is omega 2, the angular velocity. The first case that we can have is omega 1 is equal to omega 2 is equal to 0, when both the fields are stationary, that is, we have stationary magnetic fields. Both magnetic fields are stationary with respect to a stationary reference frame. So if I am standing, if someone is standing here, he will see this is also stationary, it is not rotating. This is also stationary, this is also not rotating, although the rotor may be rotating, that is a separate thing. But if we can have a case that is omega 1 equal to omega 2 equal to 0, that when both the magnetic fields are stationary in space, and that is the case of two stationary magnetic fields. So this is one way of producing torque, continuous torque. And the other way, we have only two options, right? We can either have omega 1 equal to omega 2 is imperative, we have to have that. Then omega 1 equal to omega 2 at some velocity, let us name it as omega s, say omega synchronous, because yeah, something is both are in synchronism with respect to each other. So omega 1 equal to omega 2 equal to omega s, some synchronous velocity, where they are phase shifted. Basically F1 and F2, they are not aligned with respect to each other, but they are having some angular shift of theta, but velocities are same. So two rotating things can be, two vectors can rotate like this, right? Two vectors, if they rotate at the same velocity, then with respect to each other there will be always a constant angular shift between them. So this is the second case where we have both as rotation or rotating magnetic field. Now these two cases form two different types of electrical machines. So this first case, where magnetic field, both the magnetic fields are stationary or they are not rotating at all, that is the DC machine, and where both magnetic fields, both of the two magnetic fields are rotating at certain speed, that is omega s, the synchronous speed, that is, those are the AC machines. Now in AC machines we can have, so we have the two cases, I have already discussed about DC and AC machines. Now omega 1 equal to omega 2 equal to omega s, but there is another speed, that is rotor speed. If our rotor omega r is same as omega s, that is rotor is rotating at the same speed as the rotating magnetic field, then that means our rotor is in synchronism with the magnetic field speed. So that is the synchronous machine, right? And we can have another so this is the AC machines that I am discussing as of now. AC machines, we need to have this omega 1 equal to omega 2 equal to omega s. The first case is where omega r is equal to omega s, that is the rotor is in synchronism with the magnetic field speed, that is synchronous machine. And we can have another case where the rotor is not equal to omega s, that is the synchronous speed, that is asynchronous machine, or also known as the induction machine. So we have these three classical electrical machines working on the same principle, only difference being how the two magnetic fields are and what is the relative speed between the two magnetic fields. So I think it's time now, so we'll stop as of today. Next day we'll dive deeper into these AC machines. So from AC machines also we'll see how to basically realize. We have only seen the stator realization. Next we are going to look at the rotor realization, and that will end the initial discussion on how we are basically, this is the introductory discussion on machines that I am doing. Similarly, we will discuss the basics of all the portions, different portions, and then we will go deeper into the modeling and controller design subsequently. Okay, is there any question? Then I can take that, or we can close.
Sir, in the
Thank you so much,
slide
sir.
number 7. Sir,
Slide
in the
number
slide number 7.
7.
7. So why we
Yes,
have to
yes.
extend the pole shoe? What is the reason for that?
Yes. So I'll just indicate that. Suppose we had our pole only up to this, right? Then if we have similar winding, we would have non-zero flux density only in this region. With black probably I'll show. We will have non-zero flux or some flux density in this region only. But if we extend that, then we would have non-zero flux density in this whole region. So by extending the pole shoe, what we are trying to do is extend the constant flux density
Increase the flux
region
density.
or reduce the zero flux density regions. Probably in the subsequent classes, as we go into the field in DC machine, it will become clear why we want low zero flux density region or reduced flux density region. So as of now,
Sir,
the answer is
shall
only
we
to
get it
extend the
this
region.
recording session?
Yes, yes, I expect to upload this in YouTube, and I will share the link in the WhatsApp group.
When
Yeah,
will
Samrat.
expect, sir?
I expected to do it by 1 or 2 days. Let's see. I will not edit it. I'll just upload as it is.
Can you go to the last slide,
Thank
Samrat?
you, sir.
By last slide, you mean this one?
Yeah,
10th
exactly.
slide?
Yeah. Here you have mentioned like omega 1 is equal to omega 2 is equal to omega s. So what do you mean by omega
Yes.
1, omega 2? Because I can see omega r and omega s. What I thought is that
Ah,
omega 1 is equal to omega s and omega 2 is equal to omega r. Like that I have
no, no,
thought
no.
about it.
No. What we are discussing is, say we are in the stationary. So this is the, say, axis, x axis and y axis. If someone, say, I am standing here, I am in stationary reference frame, that is I am standing, I am not moving. So with respect to me, the first magnetic field is rotating at omega 1 and the second magnetic field is rotating as omega 2. This second magnetic field, the speed is not related to rotor speed. It is with respect to the stationary observer who is standing here. Right, that is what
Okay.
by what I mean by that. That is why I have the rotor also. So I have the first magnetic field rotating, I have the second magnetic field rotating, and I have the rotor rotating. So that is why the rotor speed I have indicated by omega r. So here omega s does not mean to stator, it means synchronous speed. It is not related to speed of magnetic field due to stator. It is not that. It is synchronous speed. Some terminology I am giving. What a synchronous speed, some speed. Only the terminology, not nothing beyond that. But with
Okay.
respect to a stationary observer, first magnetic field is rotating at omega 1, second magnetic field is rotating at omega 2, and rotor is revolving at omega r.
Yeah. Yeah.
Right? So,
Okay.
if we have omega 1 equal to omega 2 equal to omega s, then there are two possibilities only. The omega r can be equal to omega s, or it cannot be equal or may not be equal to omega s. There are two possibilities. So, based on that, there are two types of machine. One is synchronous machine and another is asynchronous machine.
Yeah. Now I got it. Thanks.
Hello.
Yes.
Hello. Yeah. So now
Yes.
normally in synchronous machine, now if I can consider means like only one rotating field with respect to that is a synchronous that is one is synchronous rotating field will be there and one is a rotor rotating field will be there, right? That is only two fields will be
Yes.
there, right? In synchronous. In asynchronous also like the same thing. One is synchronous will be this. One will be the rotor's field will be there, but they are not equal to each other. Correct?
Not like that. There is a magnetic field produced by stator, say omega, that is
Correct.
revolving at omega 1. There is
Yes.
another magnetic field produced by rotor, say that is revolving at omega 2 with respect to a stationary observer.
Okay. But no. See, omega 1 and omega 2 we have told, right? So both will be there, or
Yes.
like with respect to both will be there in a now if I consider the synchronous machine. So I have
Yes.
my rotor field will be there, that is okay. And with respect to stator side, I have to consider two fields, what W1 and W2.
Yeah, basically there will be the effective field, which is the superposition of the two fields. One field because of stator, another field due to rotor. You can decompose that and see as two fields, or effectively you can see the superimposition of two fields as one field.
No.
But
I didn't understood here. What I didn't understood is like, okay, I understood that synchronous is synchronous speed will be sorry, synchronous field will be there. No, so normally stator and rotor, two parts I have to see here. So here with respect to that, like W1 and W2 you are mentioning, right? That will be always it will be there
yes,
if it is
always
a synchronous
there will
machine.
be two fields. Yes, there will be two
Yeah.
fields.
Okay, then one more field is that is our rotor field, right? Apart from
No,
W1
no,
and
rotor
W2,
is
rotor
not
field
field.
also will be there.
No, no, no. This is not rotor field. This is the mechanical speed of the rotor.
Okay,
Rotor is
okay,
rotating,
mechanical
right?
speed of the rotor.
It is rotating.
Yes, yes.
It is the it
Okay,
is the rotation, mechanical RPM, revolutions per minute
okay,
of the rotor.
correct,
This is
correct. Okay,
what I mean by omega r.
okay, understood. So W1 and W2 are that is a speed of
State.
the fields, two fields, whatever speed of the
Yes,
fields, right?
yes, yes,
Okay,
yes.
okay,
So
right.
this is the
Okay,
speed of the field of the stator. This is the field of the speed of the field of the rotor, and this is the omega r. That is the rotor speed.
okay, right, understood. Yeah, can you please write in the same slide W1 is the so that tomorrow if we are
Okay.
referring that we will not forget. So just please mention that.
Yeah. I'll do that. So this is the speed of, yes, I'll just complete it. Stator magnetic field. Omega 2 is speed of rotor magnetic field.
So can you please mention the units also?
Okay. This is the speed of rotor. So all are in RPM or RPS, whatever you can have. All are in RPM or RPS, same unit basically. Revolutions per minute, revolutions per second. Any unit you can have, all are in same unit. Or even if you want to consider radian per second, that is also one option. So all are in same
Yeah.
unit.
Sir, omega s also we
Thank you.
can write, right?
Omega s, yeah, omega 1 and omega 2 actually both are at omega s. Omega is some speed, speed of both the stator and rotor magnetic fields. So omega s is actually equal to omega 1 equal to omega 2.
So in case of now induction machines, my slip speed will be the difference, right? So there is like that whatever you have mentioned, omega r is not equal to omega s. So slip speed difference will be
Yes.
there, right?
Yes.
Okay, right. Thank you.
The rotor speed is not same as the omega s. Omega s is basically omega 1 and omega 2.
Yes,
Hmm.
yes,
Both are
understood.
equal, and that is equal to omega s.
Okay.
Clear?
And one more question I have. Can you please go to slide
Okay.
number 2?
Slide number 2.
2, I hope, but we'll see. No, 3. 3. Think. Yeah. Here in the second picture, I can see some flux which is not aiding. So can you please explain why?
What is not aiding?
At the center of the picture, I can see 2 flux lines which are not
Yes.
aiding. So what's the reason?
No, if one is in the clockwise direction, another is in the anti-clockwise direction, because both will have their own flux line, right? Similar to this. So if we have only one conductor, it will have
Rectangle.
flux line like this, and similar to that, if we have another conductor, then it will have its own flux lines,
Yeah.
right? So in the
Yes.
middle, you can see that both are opposing each other. So if one is downward, another is upward. That is why both are not aiding each other, and that is why you have, in the effective picture, you have almost zero flux density at the middle. But
Okay.
outside they are aiding each other. So if this is also anti-clockwise and this is also anti-clockwise, because both are having the same polarity. So
Okay.
here it is not becoming zero anywhere, but at the middle it is becoming zero, because if one is downward, another is upward.
But both the directions of the current are same. So
Same,
it
yeah.
should aid,
That
right?
is the key thing. Yeah,
Yeah,
what?
it's so if both the currents are on the same direction,
Yes.
basically it should only aid, right?
Yes. But in the middle it will not. At the middle between the two conductors.
You see the direction
Okay.
better.
So I'll
Okay, yeah.
draw it once more. This is dot. So it the flux lines will be like this, anti-clockwise.
Yes.
I have
Yeah.
another one. Sorry, same thing, dot only. So that will be again anti-clockwise.
Yeah.
Right? Now you look at in the middle, at the middle. One is upward, another is downward.
Yeah, it will cancel.
Yes. That is why you have zero flux at the middle.
Oh,
Zero flux density basically.
okay. Got it.
I
Okay?
have one question, sir. Last, axis of line you
Yeah.
told, no? So this will be available in the
Axis.
yeah, axis of line. This will be available in every
Yes.
like DC machine.
What will be available?
This axis of
Did not
line.
get you.
So in the DC motor, it will be available. So
Axis of line, I did not get.
yeah,
I told about the magnetic field axis. That is,
okay.
if we have a coil, then what do we mean by axis of a magnetic field? Axis is that
not crossed.
line, imaginary line, so that none of the flux lines are actually crossing it. That is what we mean by axis of a magnetic field. So axis of a magnetic field, that is what we mean by axis of a magnetic field. So one
When
line,
like ferromagnetic material in between that, this will be available,
yes,
axis of line, or else
yeah,
no.
still it will be there. It may not be a straight line.
Okay.
It may not be a straight line, but still it will be, there will be some axis.
Okay.
So in this case, if I try to remove this one,
Or else you draw in the
you
DC
can
machine
see,
last page, which you
okay, last page.
almost.
If it is a symmetric case,
Yeah.
then axis is straightforward. You can see here. So this is the flux line distribution due to a DC machine, and you see I can easily draw a imaginary line at the middle. Basically, my drawing can intersect with certain lines, but in the actual case it will not. This is the imaginary line at the middle. You can see half the flux lines are in one side, and another half is on the other side, and none of the flux lines are actually crossing this line, imaginary line, whatever I have drawn. So this is the axis. This is the axis of the magnetic field.
Okay, thank you.
This is F1, or yeah. Still now there is no F2, there is no magnetic field in the rotor. We will see how to have it so that we can have some torque production.
So what is the use of this axis?
Axis is, if you want to define the angular shift between two magnetic fields, then you have to define with respect to some reference, right? So you can
Okay.
define one direction of the magnetic field through its axis. So what is the direction of a magnetic field? Whatever is the direction of the axis, the same.
Yeah, got
Basically,
it.
the axis represents the direction of the magnetic field.
Okay, got it.
Right? Yeah.
Tomorrow, what will be the
And
flux?
one more thing.
Yeah.
See,
Yeah.
normally sir, the flux direction, like if internal,
Yes.
if it is a magnetic, if it is a magnet, so flux direction internal to the magnet will be south to north, right? And if it is
Yes.
external, means like north to south. Correct?
Yes. That is what you can see here
Oh,
also, right? When it is
yes, yes,
external, it is coming into the north, coming into south. If it is
yes,
external, again coming out of north, but internal it is south to north.
yes, yes,
So
yes, correct. Okay.
I'm not closing the lines. It is something like this, right?
Yeah.
Yeah.
And Samrat, one more thing, like at the end of the whole course, can we have some session on the FEMM usage, like how to set up some simulations?
FEMM actually
Just a overview.
already, yeah, I can give some overview, but there are already excellent tutorials available how to use FEMM. So probably I will post some links, YouTube links in the group. You can go through that, and yeah, if you have question,
Yeah, you can
you can
please
ask that.
share in the WhatsApp chat.
Yes, I'll share that.
Yeah.
There are
Anyway,
excellent
but
tutorial videos.
yeah. But one session would be doing fine, I
Yeah,
hope.
at least 1-2
Actually,
sections.
there are so many things to cover. You understand, right? We are going from, I'm starting from very basics of magnetic field due to current carrying conductor, and we aim to go at aim to reach closed loop control DC motor, and in
Okay.
between we have so many things. So
Yeah.
But
first priority
don't
will be to cover that.
Yeah,
so
I'm
don't
saying at
do
the
as
end
a
of
part of
the course.
the part of the course. Just you record
Yeah,
Thank you.
sure. I'll try to do that.
yourself, then post,
So
and we
total,
will
how many sessions
come.
might be there to cover all the syllabus?
have indicated tentatively 25. Let's see.
Okay.
Even I don't know. Yeah.
Okay, sir.
Okay. Sure. Then we can close.
Thank you.
Yeah. Thank you. Good night.
Thank you.
Good
Bye.
night.